So at this point, we have stated that the weighted ordinary least squares solution is easy to implement, but it gives biased results. And the general weighted total least squared solution gives excellent results, but is really not practical to implement in an embedded system, which is what we really wish to do. So what we do is we search for a special case of the good solution. Can we find a special case that is easy to implement? And if we can, then maybe we can generalize that special case to approximate the general solution. That's what we're going to do. There is a special case to the weighted total least squares solution. We can find an exact solution when the uncertainties on the x measurements and the y measurements are proportional to each other for all I, with the same constant of proportionality. That's going to, if we make that assumption, that's going to give us a solution that's quite simple to implement in our embedded system. That's our focus on this section, and then next section we generalize that a little bit more. So to be more concrete, we assume that the standard deviation of every xi data point is equal to a known constant k times the standard deviation of the corresponding y data point. And k is always the same. The sigma xi may be different from I to I, but the proportionality k is always the same. What we're going to do is we are, instead of reinventing a lot of math that we did for the weighted total least squared solution, is we're going to take the intermediate results of that solution, and everywhere that I had a sigma xi, I'm going to replace that by k times sigma yi, and we'll see that that really helps everything to fall apart. We look first at the chi-squared of the weighted total least squared solution, and we get this result here. The chi-squared is equal to the sum, and what we had before was little x minus big X squared divided by sigma x squared, but I substitute k times sigma y all squared, and I also have a similar result over here where I don't need to substitute anything. And now I've got things that are not really over the same denominator, but I can go through all the math that we did before, and so there's math here. There's a lot of math here. But we had a result before where I had a sigma yi squared and a q squared times sigma xi squared, and I again replace the sigma xi squared with ki times sigma yi squared, and that allows me to factor out this sigma yi from that term. And that is what ends up being key to coming up with a computable solution. We'll see that when we do the gradient of this, the Jacobian. We had a Jacobian before where I had a sigma xi squared and a sigma yi squared, but when I substitute the xi squared equals k squared sigma yi squared, that allows me to factor this term out. Why is that key? Well, I need to set this whole thing equal to 0. And before, I couldn't clear the denominator in any kind of useful way, but now I've factored out this term, which is not a function of I. Because that's not a function of I can multiply both sides of the equation by that term, and it goes away. So that goes away. In fact, the 2 goes away when I multiply both sides of the equation by it. And what that's done is it has removed q from the denominator, and the numerator is now a polynomial. And when I multiply it out, we'll do that in just a minute, but it's a polynomial, that I need to find a solution for, but I can do that. There's solutions for polynomial equations that are much easier than solutions to general nonlinear equations like the one that we had. So we're going to do that. This is just copied down there. We set it equal to 0. We multiply both sides by this term, and they go away. So I've got the sum of the numerator all divided by sigma yi squared is equal to 0. And what we're going to do is we're going to notice that I've got a quadratic equation. I've got a q times a q term here. So that's a q squared term that I'm going to write as one of these things. And so what does q squared multiply? It multiplies xi and k squared yi. So here's my q squared, my k squared times xi yi all over the sigma yi squared. That's my second order term. And I have some first order terms, which is either q times units or q times units here. The first one is going to be q times xi squared, and the next one is going to be q times minus k squared yi squared all over sigma yi squared. So that comes down here. And then finally I've got a term with no q in it at all, which is just the minus xi yi, which is what we have there. Okay, this is a quadratic equation. I'm going to call that whole thing A, I'm going to call that whole thing B, I'm going to call that whole thing C, and I've got q squared, aq squared plus bq plus c equals 0. It's a quadratic, and I know the solution to a quadratic equation looks like this. Q hat is minus b plus minus square root b squared minus 4ac over 2a, and that's great. Now, the a, b, and c terms can be written in terms of some of the summations we've defined already. And if you look at it, this a term, a equals k squared times c2n. I've already defined c2n as the summation of xi yi divided by sigma yi squared. The c term equals minus c2n. Again, c2n is the xi yi summation. Now the b term has something in it that I've seen before. The xi squared over sigma yi squared, we called that c1, but it has something new, which is the yi squared divided by sigma yi squared that I haven't seen before. That causes us to create a new definition, c3n. Oh darn, this should be a little n. Should it be a little n? No, it shouldn't. Oh, that's tricky. I'm mixing my little and my big n's, aren't I? So this n and this n need to be the same, whatever they are. So c3n is the sum of the yi squared divided by the sigma yi squared. And if we define it that way, then my b is going to be c1n minus k squared c3n. So I've got these recursive parameters that I can keep updating in a very simple way. From those I can compute a, b, and c in a very simple way and solve the quadratic equation to give me capacity. Plugging everything in, here's my capacity equation. I've got minus b plus minus b squared minus 4ac over 2a written in terms of the c1, c2, and c3 terms. Really straightforward, except for that. There are two answers to any quadratic equation. Which one do I choose? I could compute both of them, but what's that going to tell me? We know I could have two positive real roots, I could have two negative real roots, I could have one positive and one negative real root, I could have complex conjugate roots, just generally solving a quadratic. Is there any guarantee as to the type of roots that I'm going to get when I solve this, and is there any advice for which of the roots to take? So let's look at this. If you are familiar with control systems, you will certainly have encountered the Routh test before. If you are not, then I don't have time to develop it for you here. You'll have to take it on faith, I guess, that this is correct. But the Routh test tells us, generally speaking, the geometry of roots of a polynomial. It will tell you how many roots are strictly in the right half plane and how many roots are strictly in the left half plane. And you can also use it to solve for how many roots are on the axis, the vertical axis separating the right half and the left half plane. Plugging into the Routh test, what you do is you put in A there, you put in B there, and you put in C there. And then you do a series of linear algebra kind of steps on the parameters from the polynomial, and it gives you, it turns out that this result is minus C2n. That's the Routh array. The Routh test says, look at the entries in the left column and count the number of times the sign changes from positive to negative and from negative to positive. And the number of roots of the original polynomial that are in the left half plane is equal to the number of sign changes. In this case, C2n, we could either say is a positive number or a negative number. I think it's always positive, but it doesn't really matter. If we look at this, let's assume that C2n is positive. K squared has to be positive. So we assume that's a positive number. Well, if C2n is positive, negative C2n must be negative. And it doesn't matter if this is positive or if it's negative. Assume it is positive, then I'm going from positive to positive, 0 sign changes. From positive to negative, 1 sign change, 1 root in left half plane. Or if this is negative instead, I go from positive to negative, 1 sign change, negative to negative, no additional sign changes, so there's still 1 sign change, which means there's exactly 1 root in the left half plane. And we could repeat this, supposing C2n is negative. Well, this means this must be positive, and it doesn't matter if this is positive or negative, I have exactly 1 sign change. So the middle term turns out not to matter. It's the fact that the first and last terms here are always opposite signs is what guarantees that there's exactly 1 root of the polynomial in the right half plane. I keep saying left, but in the right half plane. So I've got some polynomial root in the right half plane, and exactly 1 root in the left half plane. That means that it's impossible for them to be complex conjugates. I can't have a root up here because by the fundamental theorem of algebra, I would have to have a root down there also, and that's the Routh test says that's not possible. So I have to have real roots. One of them has to be a positive real number, and one of them has to be a negative real number. We know capacity is a positive real number, so I always choose the one in the right half plane. I always choose the bigger of the two. So looking at this sign, the bigger of the two is always the one with the positive sign. So a little bit of theory, a little bit of logic, and we conclude that that is always the positive sign. And we're done. We have a computation for capacity, and that involves this C1n we've seen before and the C2n that we've seen before and this new thing called C3n, which is very similar to what we've seen before. We initialize in the same way we talked about. We say assume a synthetic zeroth measurement where the change in state of charge is 100% and the change in capacity is just Q nom. The change in amp hours is Q nom. We set sigma yi squared to a value that represents the uncertainty of the total capacity from our manufacturing lot. And going back to the definition of C3, it's going to be Q squared over sigma yi squared. C2 is going to be Q over sigma yi squared, and C1 is 1 over sigma yi squared. After we initialize, we recursively, every time iteration, update this way. We add x squared over sigma yi squared to C1 and so forth to C2 and C3. Then I put those into this equation, and that gives me my capacity estimate. Very simple to do. No drama. If we wish to compute the error bounds, we need to know what is the Hessian of this computation, and we can do that. This Hessian, again, I found this with Mathematica. It's no fun to do this by hand, but there is a general expression for the Hessian, and it's written in terms of the recursive parameters C1, C2, C3 at this point in time, which means that I don't have to store all my data to compute the Hessian. I can compute it directly from just 3 numbers. I update the 3 numbers, I recompute the Hessian, and that gives me my error bounds. The 1 sigma bounds are the square root of 2 divided by this Hessian computation. All right, well, that's nice. We can also add fading memory in the same way that we did before, and go through all of the math. I'll leave it out. It's a very, very tedious, similar math to what we've just done. And we get the same basic result, except instead of a C1, I have C1 tilde, same with C2 and C3 in the different places in the equation. And the tildes are, the variables are initialized the same way, and the variables are updated the same way that we saw for the ordinary least squared solution, that the tilde variable is lambda times its previous value plus the update factor. Again, we can find the Hessian in terms of these parameters, and it turns out to be identical in form to the Hessian in terms of the non-fading memory. I just use the tilde quantities instead of the non-tilde quantities that we used before. So we have something really, really nice. This is a special case of the total least squared problem, and it has, if this is in fact true for my system, that the proportionality between error and x and y is fixed, then this is the exact total least squared solution. And we have a closed form solution for q hat. There's no iteration needed, no Newton-Raphson iteration or some other advanced algorithm is needed to find q hat. Again, it's only simple math, multiplies and divides and adds and subtracts. The solution can be computed recursively. I need to keep track of C1, C2, C3, or C1 tilde, C2 tilde, C3 tilde. That's it. When I get some additional data point, then I update the sums and I compute the updated estimate and the error bounds associated with it. I can easily add the fading memory. All of the beautiful properties of the ordinary least squared solution we have now found in a special case of the total least squares problem. The concern is that this does not allow these variances to be arbitrary. They have to be proportionally related for this to be optimal. And that's not generally the case for us. We will often have cases where the errors in one variable are not proportional to the errors of the other, although they may be kind of proportional or close to proportional. The next section then is going to describe an approximation to total least squared that does allow an arbitrary relationship between sigma x and sigma y. It's not going to be optimum total least squares, but it does turn out, in my experience anyway, to be much better than ordinary least squares at the capacity estimation problem.